And before I begin, I'd just like to thank the organising committee for facilitating the conference in the uncertain times which we are in these days. As Barbara said, I'm Lucy Pickup. I'm from Southampton University in the Hybrid Photonics group, which is led by Professor Pavlos Lagdakis. And today I'm going to be talking to you about our recent work on optically imprinted Polariton crystals, and specifically band structure features that we have access to using this reconfigurable system. So particles subject to periodic potentials exhibit bands of allowed energies. Consider electrons and crystals, and it's no different for polaritons. But with polaritons, thanks to their part light, part matter nature, there's a whole multitude of ways in which we can actually structure arbitrary potential landscapes for them to exist within. And broadly, you can group these techniques into two categories. The first, which I'll go over quickly, is through modulation of the cavity mode and or the quantum Weld bandgap, which can be done in a few ways. For example, utilizing surface acoustic waves, as was shown in Skolnick's group in 2010. These surface acoustic waves create a periodic modulation of the cavity mode and the quantum Weld bandgap, and when they are on, it results in these band features appearing in the polariton dispersion, which otherwise are not there when these surface acoustic waves are off. Another technique that has been implemented in the past is through depositing metal onto the surface of the sample, for example, gold. And in 2007, Yamamoto's group demonstrated that using strips of gold deposited, they could produce these one-dimensional periodic potentials, and again, bands form within the dispersion. And they expanded that later in 2011 in collaboration with Sun Halfling's groups to 2 dimensions, whereby they deposited a layer of gold and then etched in these circular recesses in a square lattice, forming two-dimensional potential landscapes. Now, taking that technique of etching further, one can actually etch the sample itself, much like you would think about in photonic crystals. And this can take several different formats, whereby either the entire sample is etched, that's to say the top dBr, the cavity, the quantum wells, bottom dBr, right down to the substrate. And I show just one example here from Jacqueline Bloch and Alberto Amo's groups for a honeycomb lattice, and you can see these very nice band structures forming in the dispersion with these deep potentials. Alternatively, just the top dBr can be spatially structured through etching, and this is the example I show here is from Krasnowski's group, whereby with this lead lattice and the etched into the top dBr, they can start to see the band structure of it as well. And then, of course, there are the very new techniques which Sebastian gave the really good talk earlier about, involved on, whereby the growth process is stopped partway through the sample and the cavity spacer is etched to the desired lattice, and then the top dBr is grown onto that. And this gives the benefit that there's controllable height of the potential landscape that's created. But whichever technique of this etching is used, they have access to various different features, and recently there's been work showing access to these topologically protected edge states. First off, in Jacqueline Bloch and Alberto Amo's groups, with this zigzag of overlapping mesas, which is an analog of the Shishri-Fahiga system, such that for one of the P modes, one of the trapped P modes of the mesas, it happens that the ZAC phase of the potential landscape is pi, and so then at the boundary with vacuum, there's the formation of this edge state, this protected edge state. And then Sebastian Clemson's and Hoffling's groups have recently taken this research of topologically protected edge states in these lithographic systems to 2 dimensions, that you can access these unidirectional flows, where the direction of flow is dependent on the sign of the magnetic field, and it's robust against defects in the potential landscape that exists. But thanks to Polariton's matter component, there's an entirely new direction, not new, sorry, but an entirely different direction which one can create these potential landscapes, and that's harnessing interparticle interactions. Polaritons interact very strongly amongst themselves, but they interact even more strongly with these reservoirs of non-condensed particles that form under non-resonant excitation. And so these exciton reservoirs, their density, their spatial density is dependent on the intensity distribution of the non-resonant pump beams, and the potential which polaritons within that system feel is dependent on the exciton density. So by sculpting the spatial profile of this non-resonant laser beam, you can spatially sculpt the potential landscape in which polaritons exist. And this schematic from Jeremy Baumberg's paper using these spatially sculpted beams from 2012 shows it quite nicely. They bring two near Gaussian pumps onto the sample, and they form these two potential peaks for the polaritons in which they exist. These two potential peaks for the polaritons to exist within. And there's developing on the techniques which you can sculpt the non-resonant pump beams. All the examples I'm going to show are using spatial light modulators, but recent improvements have meant we can go from these quite simple low number of pump spots and therefore condensates right up to quite significant lattices of various different geometries. For example, here I show an image of 61 optically imprinted condensates from a paper my colleague has recently submitted. And this ability to sculpt the laser pattern enables us to access many different features of the various different potentials. But I do need to mention here that we do not need to be in the condensed state for these potentials to exist. The potential exists below threshold, but all of the results we'll show you from our work are conducted just above the condensation threshold, because that way the Polariton occupation is high enough that we can use photoluminescent across the sample, across the system, such that we can use the photoluminescence from this to characterize the various different potential landscapes quickly. And this is a typical optical setup that we utilize for these kinds of experiments. We have a blue detuned non-resonant laser, which in this case is continuous wave. And in the Fourier space, we project the Fourier space of it onto this digitally reprogrammable spatial light modulator, where we imprint our desired phase map onto it, such that when we focus it through this microscope objective lens, the desired real space intensity profile is projected onto the surface of the sample. And we use a planar sample here, and we can change the potential landscape via changing this intensity distribution just by changing the phase map that we are putting onto the spatial light modulator. Now, in our setup, we also work in reflection geometry such that we collect the photoluminescence through the same microscope objective lens and direct it into a detection path whereby we can image the Fourier space, the real space, and the dispersion simultaneously, allowing us to create and characterize these various different potentials landscapes quite quickly. So last point before I move on to the results of this work is just to highlight that for systems that are too small to show periodicity in their potential, for example, the diode as I show here, what you see in the dispersion of the photoluminescence is the spectrally narrow interference fringes. There's no semblance of any bands being formed there. But by increasing the number of pump spots and therefore the number of condensates, we can start to, we can see bands forming in the dispersion of the resulting photoluminescence. Here I'm using a system of 8 Polariton condensates that are uniformly separated in a chain. So the non-resonant pump beams are separated by the same distance throughout. And as I say, we can see these bands forming in the occupation of the dispersion. The red dashed lines here correspond to the reduced Brillouin zone calculated from the simply calculated from the separation distance of the non-resonant pump beams. And what's quite interesting to note here is that the system dominantly occupies not a ground state but one of the excited block bands. And we can actually control which excited block band it condenses dominantly into simply by changing the separation distance between the pump beams. So again, here this top row is for 8 Polariton condensates created through 8 non-resonant pump beams. It's uniformly separated. The only difference between top and bottom row is the separation distance between these pump beams. So before I move on to more intricate systems in these uniform linear chains, I just want to highlight these very intricate interference patterns that we see perpendicular away from the chain. These are Talbot interference patterns, much like those seen by Eleanor Ostrowski's group in 2016, where they were working with these chains of etched mesas. And so what this shows is that these optically imprinted potentials really have quite some potential for use in this field of research. So beyond uniformly separated chains, we can stagger the chains. And what I mean by that is we would have 2 intercondensate coupling lengths, and it would go long, short, long, short, long, short. And by doing that, what happens is these bands of energy that we had split, and this new band gap is opened, and it comes along with this doubling of the periodicity of the corresponding bands as a function of the crystal momentum. By increasing the level of this staggering, we can controllably open this band gap all the way until the adjacent bands start mixing with one another. And this is quite interesting because what it shows is that by changing the separation distance between the pump spots, we are, in a sense, you can view it as changing the coupling between the nodes in the system. And so it gives access to investigating things like the SSH systems, whereby there are topologically non-trivial phases accessible. And that is using this system where the potential is not just real, it is complex. We have optical gain in the system. Look at time, I'll move on just quickly. So in addition to these arbitrarily excited block bands that we can condense into and band splitting, we can additionally imprint defects into the potential lattice simply by changing one separation in an otherwise uniform chain, for example. So I show here the photoluminescence from 12 Polariton condensates where there are 12 non-resonant pump beams uniformly separated, except for between the central two pump beams where it's been reduced. And what you see happen in the dispersion is the formation of this dispersionless mode in the band gap of the system. What's more is when we look at the spatial distribution of these energy states, we find that this defect state is highly localized around the position of the defects in the potential landscape that we've created, and that can be seen on this lower panel here. It's interesting to note here that we are in a multimodal system because of this optical gain we have, and for the delocalized band above this defect, well, above and below, but notably above this defect state, we see a suppression around the defects of this delocalized modes. What's more is that by controlling the separation distance of this defect, keeping all of the other separations fixed and reducing that central one, we can control the spectral position of that defect state in the band gap, and it blue shifts from the bottom to the top as you reduce the defect separation size, which is very interesting. We have such fine control over features like this in a completely reconfigurable platform. Now that concludes what I want to talk about on the finite 1D systems that I've demonstrated, but it is obvious that these systems are still very finite. They're not very long chains that we're imprinting. We don't need them to see these band features, but as a result, there will still be edge effects. One could fold these chains into polygons and they can be uniformly separated, as I show on the top row here, or staggered in separations. This is for an octagon of uniform separation and staggered separation in real space and in momentum space. And we get these very nice images that we can reproduce in simulation, but it's not so simple in the experimental setup that we have to characterize the band structure that you see, because these bands now form as a function of angular modes of the system as opposed to linear modes of the system. But nonetheless, in simulation, what we can see is that going from a uniform octagon to a staggered octagon, we do indeed see band splitting as a band splitting for these angular modes of the system. And with that, I will just make my concluding remarks in that I've demonstrated, or I've shown our recent work on all optical band structure engineering, where we can controllably condense into arbitrarily excited block bands. We can split these bands by staggering the separation distances in the chains, which gives access to these topologically non-trivial phases, utilizing non-Hermitian potentials. And we have very controllable defect state condensation through optically imprinting defects to the system. If you want to read more on this, the paper's recently been published in Nature Communications. And with that, I thank you for your attention and welcome any questions.
Yes, thank you. Thank you so much. Very impressive patterns. Questions, please. Yes, Maciej.
Okay. Hello. So thank you very much for very interesting talk and very interesting results. I have a question about the very last thing which was shown in the presentation, that in the polygon, polygon design, right, of the lattice.
Yeah.
Is it necessarily the same realization as the linear chain? And my question is about because in the linear chain, you have, if I understand correctly, a nearest neighbors coupling, right, in this interference between the spots. But here, as they are distributed on the ring, they can now interact with each other inside of this ring. So,
of course.
So is it kind of like, okay, it's like a periodic boundary condition, right, along the chain, but that,
yeah.
The question is, does it change the interactions between the nodes?
So you're absolutely right. Of course, there are now the possibilities for these antidiametric couplings. But what is worth noting is that these couplings go as the sort of Polariton density goes, which drops off exponentially. So whilst you can have these couplings across the across these polygons, it is very, very, very much weaker than the coupling between the nearest neighbors. And of course, this gets more exact. It becomes closer and closer to the 1D system as you expand the radius of these polygons. But for very small polygons, there are weak antidiametric couplings, but providing that they are significantly weaker than the nearest neighbor couplings or the couplings around the polygon, then I think it's a reasonable step to not consider them.
Okay, thanks.
Thank you.
Thank you. Okay, so I think I don't see any questions more. I think we can go on.
Thank you very much.